Hi, this is Dan Bullard, retired electronics engineer. Sorry, it's been like 2 months since I did a video, but I got some kind of bug, so I'm in bad shape. Well, I was in bad shape. I'm in much better shape now. But I lost some hair. My hair turned white. My beard turned white. So things are looking up, though. Things are looking better. I want to talk about a couple things. I start every morning, I swear to God, I start every morning by going through the web looking for stuff on Harmonics, and I find the most ridiculous shit. I mean, I find stuff all over the place. It's just absolutely foolish. And Chebyshev polynomials, that seems to be the big thing in vogue these days. But, I have a video where I showed you 4 different examples of the Bullard harmonic solution predicting the harmonics of a wave, and another one, I did another video that showed you how I could determine the point of distortion in angle, and it's the only way to do it. I mean, if you ask somebody, and I've said this many times, if you ask somebody what are the phases of the harmonics of a distorted sine wave, they have no idea. No idea. Now, you already know it's 0, 90, 180, and 270. Those are the only numbers you can have. But some people believe that the phase angle harmonics are somewhat random, kind of like what they think the spectrum is random. Well, the phases might look random, but they're not. If you look at only the harmonics, you'll see it's 0, 90, 180, and 270. Yeah, all the other numbers there are random because they can be any number between pi and 2 pi, or minus pi and positive pi, something like that. But I hate complex numbers. I don't mind working with them, I just don't like them. But another thing I want to mention is this really cool proof, and I've come to this conclusion. I don't like integration, and so people would ask me if they gave a shit, why do you think law 1 is true, that the area of the distortion determines the harmonic amplitudes? And the reason is simple. I mean, I don't have to do any kind of integration or anything like that. Here's a really simple example. I have a half-wave rectified sine wave. And there's the spectrum. Okay? And if I then do a full wave rectified spectrum, so that's 2 humps instead of 1, I've doubled the area. And what happens to the harmonics? They go up by 6 dB. It's double. Okay? And so I don't need to do integration. I can see this double the area gives me double the harmonics. Now, interestingly, one thing that happens is the fundamental goes away. And so you can't really have nothing but even harmonics, but you do in a full wave rectified sine wave. And your fundamental is no longer where it was because there is nothing in the fundamental. But the fundamental goes away. And you might say, well, wait a minute, where did that energy go? Well, I already told you that the 2 humps gives you double the harmonics, right? Where does that energy that was in the fundamental go? It goes into DC. And isn't that why we're doing a full wave rectified sine wave? Isn't that why we're using a full wave rectifier instead of a half wave rectifier? We want to get more DC. That's why we're doing it, right? And so it's like, who needs integration? If you double the area, you double the harmonics, and the DC goes up by a factor of 2. It's obvious. It's just obvious as hell. You don't have to put any pseudoscientific Chebyshev polynomial crap in there. This is real life. It's really simple. It's real physics. And, these guys, I swear to God, I just did a post on LinkedIn where I told people, this is the way it goes, right? The harmonics go with the angle. Phase of the distortion determines where the harmonics go, and the dips and humps and all that stuff. And that's totally true. And if you don't believe that, you should be flipping burgers for a living. If you believe Chebyshev polynomials or some kind of crap like that determines all this shit, you know, fuck you. You're a fucking idiot. Anyway, I'm back. I'm gonna try to be back, but it was a rough 2 months, I'll tell you. Anyway, this is Dan Ballard from the river. See you later.